Thank you. Yeah. So, welcome back to the series of lectures, and probably as a quick reminder, I'm going to, we are defining, we are looking at Cartan connections from Cartan point of view, let's put it like that. This means that we work with differential forms, preferably on the base manifold, using up to gauge transformations. And the motivation of my series, at least, is that we start with some object, geometric object or geometric structure, if you wish, and we'd like to understand the invariance of this object or solve equivalence problem, for example. And Cartan connections serve as a main technique of solving this issue. So the idea is to associate naturally a Cartan connection to this object and then explore the invariance of this Cartan connection. And as a result, we get the invariance of the original geometric structure plus a bit more. So I'll skip, that's just what we had before, skipping all till where we stopped last time, which was the association of Cartan connection with a second arbitrary nonlinear second order ODEs. So we did this last time. So this was the construction, the computation that we were able to complete, and we ended up at this curvature tensor. Whereas all four coefficients can be written explicitly, and they are the invariance of our original second order ODE. And what is important here, that two of these invariants, namely B and C, so these are the coefficients in the top right corner of curvature matrix, are expressed via two other invariants. So in particular, if you want to understand when curvature vanishes, which is the same as to say when our Cartan geometry is flat, or in terms of ODEs, this means that our equation is equivalent to a trivial one, y2 prime is equal to 0, it is sufficient only to inspect A and D, so we get the result that this connection is flat if and only if A and D vanish, which implies automatically that B and C will vanish as well. So A and D are somewhat a bit more important than two others, and this is why we call them fundamental invariants. So it's a slang, so I don't want to come with a rigorous definition, but fundamental invariance is a part of the invariance that generates the rest of the invariance via some operations of,
Sorry,
that's yeah.
I will just start a Zoom.
Well,
Right?
I can speak about slides a little bit. This notion of fundamental invariance will be explored a little bit in more detail today. And the plan for today is to implement the same ideas and more or less the same line of calculations to solve equivalence problem, or at least to find the criteria, flatness criteria, for a different geometric structure. And this geometric structure will be just a free length 2 free distribution on a manifold. And I can start telling you what
Just a second.
is. I can start using Blackboard.
No. You are there. But
Okay.
no, I just jump here and this one.
Yes.
Okay. So, am I able to move forward? Yeah. Okay. So, First of all, I want to get back to the notion of fundamental derivatives, which I also call, I think, invariant derivatives in Jan's slide. That's why I left here the word invariant derivative, but that's a confusion of notation, unfortunately. As a general picture, we have a part of the curvature which we would like to differentiate. We use some analogs of covariant derivative. In case of Cartan connection, I would call it, I would use a slightly different operation which is called fundamental derivative, and it works like this. So I recall that, well, we can associate, so if you have any representation of subgroup G naught, then sections of the associated vector bundle correspond to G0 invariant maps from our Cartan bundle to V. That's the condition of equivariance, and then fundamental derivative is defined very easily. So it just differentiates the sections or these functions, the corresponding map, along fundamental vector fields, and fundamental vector fields are those which correspond to elements of our Lie algebra. So originally, these fundamental vector fields exist only for a subalgebra, if you have only the structure of a principal fiber bundle, but as soon as we have a connection, we can extend this correspondence to all elements of our Lie algebra. So the operation is fairly simple. We plug into, so the derivative now is a map, fundamental derivative now takes values in homomorphisms from G to V, because we have to choose an element along which we differentiate. Well, it of course corresponds to equivariant sections of this bundle, and well, it has a known behavior along vertical directions. This is what was discussed a lot in the talk of Jan. So there is some redundancy here, and well, you can iterate it. So you can take as many derivatives as you wish, and you end up with the same space we've seen yesterday in the talk of Jan. I don't want to analyze this in more detail. I just want to say that this is the operation that allows us to get all other invariants from a few slots in the Cartan curvature. This at least motivates us why we are interested in some particular part of the Cartan curvature, of the Cartan connection, because all others can be produced using this operation. And well, in particular, I'll use also the other term, which is called structure function. I don't remember. I think it was also already mentioned in Jan's talk, so I just recall the definition. So curvature is a two-form. Instead of speaking about two forms, we would want to speak about certain sections of some bundle, and which we can then differentiate. And in this case, it's just plugging fundamental vector fields into curvature. We got this map, and I put here G minus. It's not strictly correct because, of course, structure function, you can plug also elements from G, but as soon as these elements sit in the vertical direction, in G naught, we know that the curvature vanishes, so we can really project this into lambda squared G minus. Rather caution G by G naught, but well, from the start I assumed my Lie algebra is graded, so I can make these identifications. So in particular, this is the function we can differentiate as many times as we wish to get all other invariants of the Cartan connection. And in particular, we've seen, so this structure function would look like exactly like this in case of linear, in case of a Cartan connection associated with scalar second order ODEs. So these are these A, B, C, D coefficients. And actually, we can check that we can quotient by a subspace in the space spanned by B and C, so only A and D will be left. And this will be a part of the curvature that will produce all other invariants in case of scalar ODEs. Okay, So a quick recap. So that's what I told. So we want, so starting with any geometric structure, we want to construct natural Cartan connections. And this is a three-step procedure to me. So first one, you identify what's your model in this case. Second step, you try to understand what does it mean that Cartan connection with this model matches your geometric structure, so they aligned to each other. And then you try to come up with some normalization conditions to construct normal Cartan connection. And this is the part where, unfortunately, I have no choice but to do some algebra. That's a little bit, that's a piece I need today. This is, well, what we've seen also, I think, in the talk of Nick in the first day. So he was showing exactly this formulae. So the curvature or structure function takes place in this space. Plus means we are in a positive, so everything is graded, so this means we are in a positive degree. And we can, in a way, step 2, here consider Cartan connections aligned with a given geometric structure, means that we would want to choose a Cartan connection such that the structure function sits only in positive degrees. It's called regularity sometimes. Our normalization conditions mean that we want to put some linear conditions on our structure function, and this is algebraically formalized as we want to choose a certain subspace where our structure function takes values, and the requirements, well, that everything is invariant under gauge transformations or right action of our structure group G0. Means that the subspace needs to be G0 equivalent, and then it's an interesting, well, it's an exercise, not the simplest one, that actually we needed to be normalized. In order to define normality conditions that uniquely determine our Cartan connection, we need that this normalization conditions are complementary to the image of the Lie algebra codifferential for cochains. So it's again, so by D I do not hear the standard cochain differential. I don't give a formula here, but that's all very standard. And it enters into the picture because when you do computations, when you essentially modify your connection form, this operator tells you how the curvature is modified. And this is normally a part you can kill, and normalization conditions is what's left. That's normalization. That's a more conceptual way to speak about what is really normalization and how this works. What is fundamental invariance? As soon as you have normalized things, and another essentially structure, so Bianchi identities or structure equation for the curvature implies that this smaller part of our structure function will generate the rest of the curvature coefficients. So what is this? So in this case, D is again the same codifferential, and it now maps lambda squared G minus to G maps. It is in degree 2. So it maps 2 cochains into 3 cochains. But we need to be in the kernel of D, and we are in the normalization conditions. So we see that actually this space now becomes isomorphic to the cohomology of Lie algebras. So this is probably a very naive way to show you that cohomology of Lie algebras and in general cochain complex plays encodes in 1 and 2 cochains or 3 cochains encodes a lot of, if not all, calculations we are doing. And this cohomology, we can compute. What is important about this cohomology spaces that we do not need to know how Cartan connection looks like explicitly. before we understand where our invariants fit. If you are able, of course, to compute this cohomology. So there are some techniques. If G is semi-simple, there is a wonderful constant theorem that tells us how to compute this cohomology in terms of root systems, and there are computer implementations available. So today, anybody who deals with the case where G is semi-simple can in 5 minutes compute this cohomology even online. In particular, just understanding what your model is gives you the understanding where to look for fundamental invariants of your structures. So for example, if you were to start again, but I'm not going to do that, with second order ODEs, we can just look at this cohomology, compute it, and find immediately that there are two scalar fundamental invariants in homogeneity degree 4. And then we know where exactly, and this means that we actually would be able to normalize everything to the degree 3, and this is what we were doing using naive calculations. So this algebraic data is extremely useful as a guidance of where to look for the invariants. Yes?
Can I ask something? Okay, you have this picture for the normal Cartan
Yeah.
connection, but this picture essentially is nothing than the Spencer cohomology that you have, or when you have this structure, you have a normalization condition
Yeah.
about the canonical connection. So actually this is Spencer cohomology. It's not this, I think that is also a special property of Cartan connection. This I'm saying.
Well, Spencer cohomology normally works when your G minus is abelian, where your vector, where you have nothing but just degree -1 elements in your model. We've seen that it is quite important in many cases to, and for example, in case of projective or conformal connections, this would work, but in case of arbitrary nonlinear second order ODEs, we see that it starts to be quite important to assign different weights to different variables in order to do calculations correctly. And this is where, instead of Spencer cohomology, you need to consider this Lie algebra cohomology. And actually, these ideas come back to the original works of Japanese mathematician Tanaka, who introduced the notion of the filtered manifolds. So you have filtration, additional filtration of the tangent bundle, and then replaced essentially Spencer cohomology by Lie algebra cohomology.
But they call them generalized Spencer.
Yeah, it's even called it generalized Spencer cohomology. Yeah. Yeah. Okay, so that's a general setup. Now let's look at this setup and consider one more example. And this will be the last example in my series of lectures. And again, I wanted to choose an example that is still manageable by fairly straightforward calculations, just to give you a feeling how it works in practice. And this is free length 2 distributions. So what is a free length 2 distribution? This is it's a rank L distribution on an L times L plus 1, I think divided by 2 missing, and L plus 1 divided by 2-dimensional manifold. Sorry, it should be so L plus 1 divided by 2. We'll see where it comes from. So it comes from L minus 1 divided by 2 plus L. This is the dimension of the manifold. The vector distribution has to be bracket generating. Moreover, it has to generate all tangent space already after taking first brackets. So we want to have D plus the square plus vector fields in the brackets of D to span all Tm. And more explicitly, if we choose local frame that spans this distribution D, then this vector fields should span Tm at a point, and actually if you count them, you see that they have to be also linearly independent at each point.
We assume J is less than K.
Yes, well, we all know that Lie bracket is anti-commutative. This is why we have L times L minus 1 by 2 here. Yeah, indeed. So I'll be using this fancy notation where instead of taking care whether G is less than K or greater than K, I use these brackets, which means that we can interchange J and K, but this changes the sign. Uh, so we introduce this notation. We, for some reason, which will be clear very soon, I put minus here. And I say that, yeah, so this is our structure. And not all structures, not for all structures we can find nice Cartan connections, but in this case we can. And how can we find the model homogeneous space? To find the model homogeneous space, we look for the simple. I take a naive approach. I'll speak about like more conceptual way of doing that a bit later. But the naive approach says, let's look for the simplest possible object in what we are considering. So what would be the simplest possible object? And I say, well, probably the simplest way is when we take some vector fields xi here, we take brackets, we get new vector fields, but all other brackets would vanish. So nothing else. It's like an analog of considering trivial second order V, y2 prime is equal to 0. In this case, of course, if you take arbitrary vector fields that span D and take brackets and start taking brackets between further brackets, we will get some non-trivial relations between those vector fields, computation relations. But let's assume they are all 0. Then we will have a Lie algebra. So this xi and xjk will form a basis of nilpotent Lie algebra because it will, well, actually length 2 Lie algebra. And what will be model distribution? Well, we just take left invariant distribution on the Lie group that corresponds to this Lie algebra. And that is something we can always compute more or less explicitly. And then as a model, we take the full symmetry of what we get, of this flat case. It's again, it's a matter of how one can compute this. Actually, this is not how I was constructing this model. I'll tell you later on where this model may be recovered, or how it can be recovered in a much more conceptual way, algebraic way. But this at least works. And this is a model. So it's a bit probably unexpected that you start from fairly simple data and you end up with yet another semi-simple Lie algebra, so LL plus 1 in this case. And I give here under a suitable choice of, if you choose your invariant scalar product to be anti-diagonal, or appropriately anti-diagonal, so probably you should have it, should choose this to be like this. All zeros everywhere. Then you recover that your Lie algebra becomes like that. So it's n by n slot, then 1. So n, we split the dimension 2L plus 1 into n, 1, and n. And this is our subalgebra G0. For some technical reasons, I prefer to keep it lower triangular this time instead of upper triangular. It's equivalent thing, but it just makes things a little bit easier to compute. So again, the grading is given as in case of a cell 3, according to how far we are from the diagonal. So 0 degree on the diagonal plus 1, minus 1 in this case over the diagonal, and minus 2 at the top right corner, and plus 1 plus 2 below the diagonal. And well, some matrices, some of these coefficients are of course matrices, and some they have some further restrictions like y and t, for example. Y and t are matrices that are skew symmetric in this case. Actually, yeah. So now we try to play the same game as we did. So we would now understand what does it mean that a Cartan connection with this model matches with the data we have with a free rank L distribution. So now we are not in the flat case. Now we are in an arbitrary case, which means that this vector fields no longer commute. As we need to deal with differential forms, it's convenient to switch to a dual coframe. So these are the forms that form dual coframe. So in a way, fixing a frame, x1, etc., xl, is as if we fix certain coordinate system in case of, for example, ODEs. So you just use, this can be, if somebody gives you a rank L distribution, you can always do that by your favorite choice. It's in no way canonical, so it's just some data that encodes your structure. So by dperp we denote the one form that annihilate our D. So then standard calculation says that d theta gk will be equal to g theta g theta k modulo and some terms which include theta rs here. So it's that just reflects the fact that we've chosen our frame that xij is a bracket of minus xi xj, and the rest is unknown. So to be explicit, we have this thing. So if you write now complete structure equations for a given coframe, these are all the coefficients that show up. Essentially, these are the same functions with a modulo the sign. Well, these are the functions we have. So these are the same functions up to signs that will show up if we take brackets between the frames. So xi and xjk, if you bracket them and expand through the given basis, or if you take xi1, j1 and xi2, j2, take brackets between them, again expand. So it's a huge number of coefficients. And as everything was chosen in a not canonical way at all, so it's not clear what of these functions is important, what is not. What of them, which of them are invariants, how they behave. Well, of course, we can now play the game, like change a different frame or coframe, see how they change, try to find out what is preserved, what is not preserved, try to write Jacobi identities or Bianchi identities, if you wish, and structure functions. So differentiate it once again and see which of these functions show up as differentials of some others. So that's always available, but we have Cartan connection. Well, we would want to have Cartan connection at hand, and we would want to use it as an instrument to do such calculations in a much more conceptual way. Let's put it like that. So how does this work? Now let's choose a connection of our associated with our model, G by G naught. So again, we choose any section and we write our connection very explicitly in terms of the collection of one forms on the base manifold. So we need to understand what does it mean that it is aligned with our structure. And again, it's easy to see that these forms omega ij that sit on the top right corner are transformed linearly under gauge transformations. So the span of these forms does not depend on the choice of the gauge transformations and variant things. So orthogonal complement is also well defined, and we say that our connection is adapted to the distribution if the annihilator of these forms is exactly our distribution. That just makes sure that we associate our Cartan connection with the data we have on our base manifold, or structure we have on our base manifold. Yeah, so we did choose some coframe, well, non-canonical coframe before. In this coframe, we had dperp equal to also orthogonal complement of theta. So the question is, maybe we can make sure that omegas and thetas have the same modulo something. And what we can do, and now we start adjusting our section to make sure that maybe forms omega are aligned with forms omega, at least this one's omega i's and omega j's are aligned with forms theta as much as we can. And first of all, we can ensure that omega i's and theta i's are the same modular d perp, so modular these terms, which are the same here. And that is just by playing with G0 part of section. So G0 part of our section, it takes part in GLL in this case, general linear transformations that transform omega i's arbitrarily in a linear way, so we can ensure that omega i's is the same as theta i's modular some other terms we have. And this defines our section uniquely up to terms of degree 1 and 2. And now we start computing a structure function or curvature. So we start with highest degree here, so it will be degree 1 in this case. So we take the part of the curvature that sits in the top right corner, and well, again, it's standard calculation. So as I say, so we want our structure function to have no components of degree well, it should be less than 0, sorry. So assuming we have only components of degree positive, they are less or equal to 0, yes, sorry. So then we check what happens, and this tells us that actually this slot has to be 0 modular d perp. So this is these two forms are in d perp. So this term should vanish modular d perp. And in this case, theta I, theta j is the same as omega and omega j. So we can actually guarantee that omega j's and theta j's are the same. So but that follows from the conditions that we want our structure function to have only positive elements of positive degree. So we have achieved already quite a lot even from the start. So we aligned already omegas with thetas, and we've chosen already, we've been able to choose a section in a unique way up to degree 1 and 2. So what next? Let's now see what we can do if we want to further make changes to our section. And if we just modify a section by terms that lie in exponential map of G1, so essentially we exponentiate elements from G1. So it shows, it turns out that omegas are transformed in this way. So I recall that omega i's were the same as theta i's modular omega theta ij's if you wish. So we can assume this thing. And we also try to see what happens next. So we try to pick up some other coefficients which are in omega ij. So this is a G0 slot of our connection. And we see that these coefficients change like this. So this is the transformations, these are our gauge transformations in this case. And again, well, we can do a few things here. We can, for example, well, the choice that was that we made some time ago was to kill the trace of this coefficients A, I, J, K. So we can always assume that it's trace free, and this will determine our section uniquely up to degree G2. So computing further curvature, we get more and more tensors showing up. And we can, well, what is the advantage of the thing? So we can compute them very explicitly in terms of the structure functions of our non-canonical frame. So some structure functions of our non-canonical frame start to show up here. Here, P and Q are curvature, and A and C are still coefficients of our connections that we are building. So we are trying to solve, we are trying to find A and C in such a way that this P and Q are as simple as possible. And And we can first of all annihilate this thing. You see that we have a lot of freedom in A and C to make sure that this is 0. So then A and C coefficients become linked to each other. And finally, the other piece of our curvature is transformed now in this way. Again, it requires some skill to write all this correctly with all these brackets, but it's still not very difficult calculation if you do it carefully. So the question, and the coefficient A is what is left undefined in degree 1. So, well, at least in this part of the curvature we still consider. And of course, we see that A has just 3 indices, this thing has 5 indices, so at most we can kill some traces. And that's exactly what we can do. So if L is greater or equal to 4, and I'll speak about case equal to 3 a bit later, so we can actually uniquely determine A by the condition that, well, first of all, we've chosen a section such that it stays free. And second, we make sure that P is trace free, totally trace free. There are a few, I think, several traces available here. So we assume it's totally trace free. And these two conditions uniquely determine us A, and the C was determined before, so C was determined here. So this already determines us completely a part of the curvature in degree 1. And
sorry, let's go back one slide. So where do P and A appear in the which form is this?
so P and Q show up here.
That's the definition. Okay.
So this is a G0 part of the curvature, and Q shows in G minus 1 part of the curvature, but Q appears as the forms omega r omega s, so it maps elements of degree -1 and -1 into -1, so it's degree 1. And here we have elements of degree -1 and -2, and they map them to elements of degree -2, so it's also degree 1.
But where did the A's originate?
A's originate from their form Cartan connection. So A and C are unknown coefficients on the base, and these are these are part of the curvature. Part of the Cartan connection we are trying to find, to compute. So we are solving. Again, we have equation. We have imposing some normalization conditions. We are trying to uniquely determine our connection form, and in this case, we are trying to uniquely determine tensors A and C here. And how do we do that? We show how A and C show up in the curvature. This is the formula. And our normalization would be then Q equal to 0 and total trace of P equal to 0. So these are again, the purpose of this exercise is to show that even if we are dealing now in a very much more complicated case, the general, conceptually we do the same calculations. And the Lie algebra and the model of our Lie algebra guides us. What do we need to compute and how do we need to compute things? So that's what we get. And what is really important here, that this total trace-free part of this thing is the only fundamental invariant for in case where rank of the distribution is at least 4. And I recall that these functions, we determined these functions first from an arbitrary coframe associated with our distribution. So it's a very efficiently computational. So if you can effectively compute the things, choose an arbitrary coframe, take brackets or coframe, whatever you prefer, compute this f, and take the theorem says that only total trace-free part of the thing matters, and this is invariant. And moreover, our distribution is flat, equivalent to the standard one, on left invariant on the Lie group, if and only if the total trace-free of the thing vanishes identically. And the reason why I've chosen this example and L equal or greater or equal to 4, because we can stop here. And this is a rare case where, well, rare case. This is a case where every calculation stops at degree 1, even if you haven't yet computed the rest of the curvature and haven't yet computed the rest of the Cartan connection. And the only reason why this works is exactly because we can compute effectively the cohomology I spoke about. So this cohomology is, in this particular case, is concentrated in degree 1. So it is in degree 1. So this tells us that the fundamental invariance, there will be only one tensor or fundamental, oh, no, maybe many, but we recovered one, that it will be in degree 1. So the rest, even if we haven't yet computed it, will be can be computed as fundamental derivative of this piece. So this is an extra algebraic data. I don't show you how we compute this cohomology in this case. And again, I refer to Cartan theorem and calculations that. So I say that it's computed via Cartan theorem, which tells us how to compute such things for G simple or semi-simple. So this is a piece of algebra, but again, a piece of algebra. If you to use the power of this theory and the Cartan theorem in particular, you of course need to understand basics of semi-simple Lie algebras, at least on the definition level, basics of what is a Lie algebra cohomology, but the rest is really done by certain online tool, if you wish, or computer. Can be done, unless you of course want to understand better or deeper what really happens inside. In this case, it's sufficient to understand that the fundamental invariance lie in degree 1. Well, I have a few minutes left, and actually I have a disclaimer here. So I should have put names on this theorem, and this theorem was proven by me and Jan Slovak back to, I believe, 2011. Sorry for not putting names here.
Earlier?
Maybe earlier, yes. In the scope of generalizing some other results in low dimensions. And what is the other cases of free distributions, which are certainly of big interest, but that would require many more computational, it will require much more time, and essentially would not provide any additional conceptual information on how one constructs Cartan connections. So most probably well-known case is what's called free-length 3 distributions of dimension 2. So these are 2-dimensional distributions of 5-dimensional manifolds, and 3 means that if you take 3 brackets, at most 2 brackets, you span all Tm, and these brackets have to be linearly independent. So x1, x2, bracket of x1, x2, and then one more bracket you may form. They lead actually to also a Cartan geometry with where your group G is semi-simple or simple. It's G is in this case 14-dimensional exceptional Lie group of type G2, split form. And surprisingly, I think the very first person who found it was also Lie Cartan back to 1911. And I recall that I started my lectures by saying that Cartan connections were first introduced by Lie Cartan around 100 years ago. So this is certainly older than 100 years. So at that time, actually, what Cartan did, he didn't use the language of generalized spaces, as he called Cartan connections. He only used so-called Cartan's equivalence method, and he did associate 14 forms on a certain bundle with this geometric structure, with this data, and that was done very much in the same. Well, no, it was done not via the way I'm telling you. It was done via different technique. And moreover, at that time, Cartan didn't bother whether it's a Cartan connection or not, which means he didn't bother whether you get something which is G0 equivalent or not. And it was not. So it took some time for people to understand that minor corrections of Cartan calculations would actually ensure that you end up with a proper equivalent form with values in this exceptional Lie algebra G2. The other interesting case, and this is dimension 3 again, sorry for misprints. So free length 2 distributions of dimension 2 are not interesting because they are exactly contact distributions on three-dimensional space. I mean, not interesting, they are of so-called infinite types, they don't possess finite dimensional symmetry algebra. So in dimension 3, we have the same model, but the cohomology looks different, and the fundamental invariant shows up only in degree 3. So I would, if I were to compute this fundamental invariant for three-dimensional distributions, I would need to do 2 more steps of calculations. It's again not something terribly difficult, but well, it would take much more time. And finally, I promised to tell how actually one can go to the model from just a vector distribution, and this is due to Tanaka. I mentioned already the name of this Japanese mathematician who actually, well, tells, or his works were devoted to the concept of filtered manifolds. So when you have a bracket generating distribution, you generate a filtration, then you take an associated graded space, you get an important graded Lie algebra that is called a symbol. And then there is a procedure which is fully algebraic, and it is called today Tanaka prolongation, or we've seen this construction in the work of Andrei on, he called it Cartan prolonged, but that's identical procedure that would allow us, just by looking at the G minus part, to recover all G. So it's a purely algebraic thing. And this is what probably I would do if I were to understand what the model is. And finally, if G turns out to be semi-simple, and actually in all my examples I showed in the lectures G was semi-simple, you have an additional, much more powerful technique that comes from the structure of Lie algebra and the fact that it has non-degenerate Killing form, for example, and some other nice algebraic observations. So you end up with the scope of so-called parabolic geometries, and parabolic geometries are Cartan connections or Cartan geometries which are modeled by parabolic homogeneous spaces, or sometimes called generalized flag homogeneous spaces, varieties. This is the case where G is semi-simple and P is parabolic, as it was in all my examples. And I cannot avoid citing the excellent background in general theory of parabolic geometries. So this is a book where you find all the details and maybe also all the examples I was speaking about, but in the scope of a more general framework of parabolic geometries. Okay, so I'll stop here.
So I would like to ask, in general it's known that not only you know that that the cohomologies tell you where the harmonic parts of the curvature are, the essential one, but also we know that there must be a natural differential operator which hitting these will provide the whole curvature.
Yep.
Is there some way how to get it in an effective way, or?
There are there is a naive way that's use Bianchi identities, but that is like case-by-case analysis and a heavy calculation. Or I would say that there is this splitting operators and that I think provide the recursive formula to recover a full structure function from a part of it. And I refer to probably Andreas Job as a specialist on this topic. Unfortunately, I never was able to use it efficiently, so my way was always naive one.
I mean, in the conformal geometry, everybody knows. So you have the wave part of the curvature of any of the wave connections, and then you make the trace of the gradient, and that's the Cotillard.
Yep.
So this is an example, but there it's easy.
Yep.
If the dimension is bigger than 3, right?
Yep. So I think that is what we started discussing back 10 years ago, but then never able to finish. So maybe in this particular example of free distributions, that's something that has to be.
Maybe an additional comment, Boris didn't mention, but it goes back to what we heard also from Dennis yesterday. So this very free length 3 distribution, so 3, 6, is a very rare example where the group of automorphisms of the homogeneous model is bigger than the G itself. It's one of the very few examples. That was our motivation to study it, right? Because we wanted to see there's then the strange version of the Pfefferman construction, which gives you another geometry on the same manifold. That was the Bryan thesis.
And well, I didn't put a reference here, but if you go to Archive and look for a joint paper of me and Jan Slovak, that will be the only one, I believe.
Okay, some other question? Okay, if not the case, let's thank again Boris Doubrov. So next topic.